Yes, here we are once again. It is the physics video lecture. Psci 168 video lecture 13. So we've been talking about satellite orbits and we're going to move, I'll do a little review on that, but we're going to move into Newton's laws of motion. We tie everything together today. We learn about kinetic energy. We're going to make it back to energy, but first we have to talk about Newton's laws of motion. So the first step, though, I'll just briefly review satellites. And remember, I sent you guys off last time to find as many nice and relevant images as you can. So you're going to always want to do that. So in the satellites discussion, here's our central body of radius r. You know, we're launching there. It's a near Earth orbit. Okay. So we're circling the Earth because we've thrown the thing with precisely the speed so that when it falls, it just falls around. Right? In essence, this is a small picture, but we've seen enough of this, right? In essence, it goes forward and falls at the same time. It's constantly moving forward and falling at the same time. So good, we discovered that for the Earth, a near Earth orbit has a speed of approximately 7,900 meters per second, which is pretty fast. And if you've solved for the period of orbit, you found it was around 1.5 hours. Right, we talked about that. So this needed the science of motion, right? We had to study motion in order to be able to accomplish this. So we used motion. We used uniform motion forward and free fall accelerated motion. So motion, comma, uniform and accelerated. Okay. And uniform motion, you can just say distance equals v times t, but accelerated motion, you say the height something falls half gt squared. So there are two different laws of motion. We learned about what g is, the gravitational acceleration. And if I want to continue this train of thought, I might say, now, how do we even get an object to move this fast? Obviously, that is faster than the strongest arm can throw. We need rocketry and we need an understanding of forces and motion. So we'll formulate this as a question. How to achieve these high speeds? How to achieve these high speeds and put a satellite in orbit and place satellite in orbit. There's our question, how to do that. And we have to understand force and motion. So the topic that we're going to cover now is force and motion and the famous laws formulated by Isaac Newton, Newton's laws of motion. Newton's laws of motion. And we're going to concentrate on the second law. I'm going to send this up here, keep my numbering scheme going. So 4 would be Newton's second law. I'm going to write directly underneath here, mass times acceleration is equal to a net force. what this law does, now, acceleration we've just studied, right? Accelerated motion, free fall. So this we know about. This here, we also know about. We studied forces in a number of different ways. We were able to talk about structures. Okay, so in fact, let's go ahead and put arrows on this. It's a vector equation, and we've also studied vectors. So force is a vector. A net force is a vector sum of forces. So the new quantity here is the mass, and mass is a resistance to a force. It has the property of inertia. So mass has inertia, and inertia we'll define as resistance to a change of its state of motion. So inertia, resistance to a change of the state of motion. So if a mass is at rest, it wants to, we're going to say it wants to stay at rest. Now, one of the best demonstrations of this, I'm just going to recommend to you guys. Suppose you're up at a lake somewhere at a lake or a dock, and there's a boat. We can be talking about anything from a rowboat to a yacht, pretty large boat. So I'm going to draw a boat here. There's a boat, say there's a sailboat, or it could be a rowboat. Okay. Point is, if you ever have a chance to come up at a boat at a dock at rest and give it a push, it's going to move away, it's going to float away with very little friction involved, and you can get a feel for what it means to exert a force on something and really feel that inertia. Okay. You can't do that with a car because there's just too much friction. So I'm just going to write here, test inertia and force just by pushing or pulling on a boat. It's it weighs tons, it's in the water. You can push and pull on it and see how it responds to force. Okay. Test inertia and force by handling. Don't let the owner catch you, okay? You want to be in the right circumstances. By handling a boat at the dock. Yeah, that's what I'm telling you. If you push and pull on it, you're going to feel what this relation is all about. Now let's go ahead and just take the simple form of this equation and solve it for the acceleration. So from Newton's law, Newton 2, this is Newton's second law, okay, right here. We can solve for the acceleration. It's equal to the force divided by the mass. So the force is the force in your arm, okay? The larger the mass, the smaller the acceleration, okay? If the mass is smaller, you can accelerate it more rapidly. And remember, the acceleration is the change of the velocity. If it's starting at rest, you get it moving, you're accelerating it. So this is the kind of thing that you can get a feel for. We're going to use this law, and I'm going to continue with it. Let's talk about the units of mass. So are we numbering things? Yeah, we're numbering things. That was 4, this was 5. Good. Like I said, you can't do this with a parked car or something. It's just too hard to get going. Okay, you're really working against friction too much, but if something just glides, you really feel what's going on here. Okay, so moving right along. The unit of mass is the kilogram. Okay, And I brought a kilogram to class. I'll hold it up to the camera. Fine, good. Let's go ahead and erase this. Okay, so continuing on here, the unit of mass is the kilogram. Now, this is Newton's law of motion, right? Motion here, but it also holds true when things are at rest, okay? Because then you would say that net force is equal to 0. But talking about the left side here, the unit of mass is the kilogram. So I brought a chunk of metal to class that we've been calling a 10 Newton weight for a while, and but it's labeled kilogram for whatever it's worth. This is a unit of mass, a kilogram, and as you can see, it's weighing about 10 newtons, as we had seen before. So what else has a mass of 1 kilogram? So I'll go ahead and draw this mass here with the hook. That's 1 kilogram. Another mass of kilogram, so this is example 1. Example 2 is even more important. A liter of water has a mass of 1 kilogram. So you can always get a little plastic bottle, liter bottle, fill it up, maybe back off a little bit because the bottle itself weighs something. But 1 liter of water has mass m equals 1 kilogram. So you can always get a test sample of 1 kilogram just by having a liter of water in a thin plastic bottle. So yeah, I'll draw this water bottle even. So oops. What's my generic water bottle look like? There, it's a bottle, 1 liter. And because this is the metric system, things are pretty nice. 1 cubic meter of water equals 10 to the 3rd liters. Okay. So another way to get a liter, so here's a cubic meter, and of course there's the meter stick, right? So it's 10 to the 3rd of these little cubes, which would be a liter cube. And since it's 10 to the 3rd, it's 1/10 of a meter cubed. So a liter is this, this orange section here is 10 centimeters. You take a cube of 10 centimeters, that's 1 liter. Okay, that's a unit of volume. Meter cubed, 10 to the 3rd liters equals 1,000 times 10 to the minus 1 meters cubed. So 10 to the minus 1 is 1/10 of a meter, 1/10 cubed, and of course you can see 10 to the minus 3 times 1,000 is going to be equal to 1 cubic meter. Okay, so that would be your liter as well. So yeah, the metric system being a decimal system, very, very convenient. And since a liter of water has a mass of 1 kilogram, a cubic meter of water has a mass of 1,000 kilograms. And 1 cubic meter of water has mass equal 10 to the 3rd 1,000 kilograms. Okay, that's going to play a big role. I have to say one more thing. The mass is often written with a lowercase m, even though the meter is also written with a lowercase m. You just have to pay attention, Okay. Sometimes you use the uppercase M to avoid problems, but it's often enough, like right there, I spontaneously wrote the lowercase m, it was up there as well. In that situation, it's mass, and here it's meters, so we'll just have to pay attention to that. So good, that's the unit of mass, it's the kilogram. Now we're going to take this knowledge here back up into this equation and discuss nothing other than the following situation. Imagine instead of a metal piece here, I have a piece of string connecting, or imagine I have a little loop of string connecting our kilogram to our scale. And then what I'm going to do is talk about cutting that loop of string and see what happens. Okay. This is a demo, so to speak, that we just have to talk about in terms of Newton's law. So, assuming this numbering is still working out, I'm going to leave this up because it's so important and put 0.7 right here. So I'm going to call this a demonstration. It's a thought experiment, if you want. So 7 demo, we hang a mass and cut the string. So when it's hanging there, it's at rest, and when we cut the string, it's going to be in free fall. So I'll do this in 2 parts. First part, here's my scale, here's my mass, it's looped with a string here. And this thing happens to say 10 newtons, or just some number. I really don't have to put that number there. What I'll say is I have the weight, and here I have a tension. Okay, so the weight is going to be lowercase w, tension is going to be uppercase T, and I'm going to have T minus W. Wait, let's do this. I'm going to have net force equals mass times acceleration for both of these demonstrations. Got to go ahead and get rid of this after all. Okay, so here's the thing. The net force is these 2 arrows. Make them red. One's pulling up, one's pulling down. They equal 0 when you add them up as arrows. So we have T minus W equals 0. That's before we cut the string. So part 2, we're going to cut the string. Good, so we cut the string. Now my scale is now empty and it reads 0. My mass here, it has the weight, but it no longer has a tension, okay? I'll just imagine it's a string, it's just a string like that. No tension, because I cut the string. So what does Newton's law say about this second scenario where I cut the string? The net force, there's no tension, it's now just minus W equals M times A, okay? But the acceleration is the free fall acceleration, so that equals M times minus G. So we cut the string, no tension, weight W, and this thing here is in free fall. So that's why I put in the free fall right there. And here's what we learned from this. if I equate these two expressions here, this equals this, what do I get? Minus sign cancels, I get weight equals m times g. This is the whole punchline we are after here. Weight, so W equals m times g, or weight equals mass times the acceleration due to gravity. Such an important expression here, and here it is in the lower right-hand corner, but I'm going to showcase it some more. So weight equals mass times gravitational acceleration. Okay, this is utterly important. So that's what we learned from this, from Newton's law that we inherited from Newton. I don't have a quick derivation of this by any means. Okay, this was epochal because it linked forces and motion. Okay, with this concept of mass, so we applied it to our very simple object here, object of it's massive and free falling, and we learned that the weight has this expression. So I'm going to go ahead and showcase this. That'll be number 8. And I'll say a couple of words about it. So we had to go through motion and free fall to get this important expression here. Because I may have used the word mass in the past, but I was trying to avoid it until we could formally introduce it. So now we have the concept of mass, and I'm usually not going to write this W for weight anymore. We have other symbols we need the W for, other concepts. Whenever we have a weight, we're pretty much always going to write m times g. Okay. So once again, I'll just write it out in words. What do I say? Weight equals m times g. So suppose we have this same mass, it's a kilogram. Okay. So example, 1 kilogram on Earth weighs 1 kilogram times 9.8 meters per second squared, 9.8 newtons, right? I've been talking about 10 newtons, really 9.8 newtons. But what if you take this same weight up to the moon, okay? Up on the moon, so 1 kilogram, and it's the same thing. It's a hard chunk of metal. It could, could do whatever damage a piece of metal can do. Nonetheless, 1 kilogram on the moon weighs 1 kilogram times approximately 1.6 meters per second squared. So that would be 1.6 newtons. Oops, 1.6 newtons. That is to say, if we took this spring scale to the moon and this weight, we proudly stand in front of the camera, and on Earth it would have been down here. On the moon, the scale would show this. This weight would be much, much less, because the weight comes from the gravitational acceleration. Now, if I go back to that sailboat, if I have a boat, so here's a second example. Now, returning to the boat here in the water, right, there's the boat, got the sail. Okay. The boat in the water, it has a weight. It's just kind of like the mass on the scale a minute ago. It has a weight here. I'll just write capital mg. And the buoyancy force, I'll write it out, buoyancy. The buoyancy force counteracts the weight, and therefore it's just floating there. So you could say the net force is 0, and if you push the boat, okay, you give it a push from this side, it just drifts forward. Okay. So this weight can be enormous, but of course the buoyancy force is holding it up, and therefore it's essentially 0, and you can just give it a push and it drifts away. But because it's a boat and it's not, it's massive, you really have to put some muscle into it. You feel that resistance. Good. So this was utterly crucial. We related force and motion, and we saw that mass times acceleration. Again, the general expression is here. Force is mass times acceleration. So this is the static case, you could say. If it's just hanging there, you cut the string though, and the acceleration is now a dynamic case, and it's falling mass times acceleration. Okay, let me consult the clock here. This is pretty theoretical, but we're trying to leave nothing out and avoid any real technical difficulties, but this is absolutely crucial. So my next idea and demonstration is going to be the following. Suppose we have this mass, and it's up a meter, and then we drop it, right? I had argued in the past that if I drop this thing on a nail or on a spike, I can drive the spike. Remember, now we're going to go back to work to talk about the concept of work. I lifted this thing up 1 meter. There it is. I did 9.8 Newton meters, 9.8 joules of work. Now if I drop it, it's going to come down again. It's going to pick up speed. So that's what we're going to investigate now. So we got the weight, we got these examples again. So now again, I'm calling it a demonstration, but it's a demonstration in your brain. The object here, so let's go ahead and give ourselves an x-axis. I think what I'll do is open up a full board demo. I'll just say drop a mass, and I'll get a little more space up there. So we're continuing with point 9 here. Okay, I'm going to talk about dropping this mass. What I want to do is have a vertical x-axis now, so we're measuring it in meters, and this will be the 0 level. And first, we're going to lift a mass, and here's the level h. We're going to lift the mass so that work W equals force times displacement. So we're getting back to the energy and the work concept, but now we know the force is a weight, so it's M times G times H. This is something we're going to look at quite a bit. Okay. Very simple expression. Work is the mass times gravity times H. So remember your definition of work. Force times displacement, lifting something. Good, so here's our 0 level, and we lifted we'll make it this guy right here. Okay, we lifted it up to this level H. Okay. So the second thing is drop the weight, drop the mass. And the question is, how fast is it moving when it hits the bottom? The speed at impact, and by impact I mean when it hits the ground, is, I can do that in 2 steps. I had the answer before, but we haven't talked about it for a little bit. So the speed at impact is obtained with h is 1/2 gt squared. So the law of free fall, and v is equal to g times t. So when we plug one of these into the other, we get h is 1/2. Put the g in the numerator. The t is equal to v divided by g. We square it, and we get one of the g's cancels in the numerator. We get v squared over 2g. Okay. So the speed of impact is right here. We have a relation h is equal to v squared over 2g. Okay. So we can say we know what v is. It's the square root of 2gh. But that was just from the law of free fall. So work is equal to mgh. At the moment of impact, all of that work has been converted into something. And this thing is moving, and it can drive a nail. So what do we have there? Let's just rearrange this thing. So we have mgh. I'm going to continue on the next board. I'm just going to continue that equation up there. So was I numbering things? Lost my numbering. That was 9. Let's just make sure we have that here for the record. 9. And now I'll continue right under here. This is great. So 3, continuing 9. Now the work is m times g. Now let's just plug this h in here, okay, which is v squared over 2g. V squared over 2g. The g's cancel. And we end up with 1/2, there's a 2, m, the only thing that's left over is v squared. So look at this. This is the same work. It's been converted to what's called kinetic energy. This is an object in motion. It has the same amount of energy as the thing that we lifted, now been converted to motion. So this here is called kinetic energy. And I'll give a definition, start a new number here, 10. Kinetic energy, energy of motion. And since this is an important definition, I'll just write capital K, or I'll either use capital K or KE. Sometimes I can do that interchangeably. 1/2 mass speed squared. Okay, you'll see we had to do all of these things in order to get to this important definition. Remember, we had already talked about work, the grandfather clock, we even talked about power, but the motion aspect is so important. For that reason, we had to study motion, and first I'm going to consult the clock, but then I'm going to immediately talk about a really interesting application of this. So, consulting the clock. Yeah, this is perfect. I'm going to end with a dramatic example of kinetic energy. So yeah, we have a mass, and the 2 just came in for formal reasons, we saw it before, times a speed squared. So you could ask, what has kinetic energy? If you drop this chunk of metal here, that has kinetic energy as it's falling. You throw a baseball, it has kinetic energy. A moving car has more kinetic energy. But the example I want to leave us with, and we'll turn this into the next project, what about an asteroid moving through outer space and colliding with the Earth? It has a half mv squared, but the mass, say this asteroid is as big as a building, okay? It has a lot of mass. What kind of a speed do you think the asteroid has? Okay, think about that. How fast is an asteroid moving that came from the far reaches of space, fell down to the surface of Earth? Well, we have an estimate of it because we know how fast an orbiting body has to move. So an orbiting body has 7,900 meters per second. Okay. Asteroid coming out from the far reaches of space is going to have at least that much, okay? Because it came out from a great distance. If our orbiting body were going faster, it would move out to a great distance, okay? So those things are reversible. So if we take a half mass of an asteroid times v squared, that is an enormous amount of kinetic energy. And what can it do? It can dig a crater. So I'm just going to leave us with this idea, and I'll even start some homework on it already, namely to get some images. Okay. So I'm just going to write here next. The Arizona, pretty sure that's what it's called, or you can look this up, Arizona meteor crater. It's supposed to be a C, crater. Look this up, okay? This is one with images and dimensions. So, homework. And this is an interesting thing to read up on. You can find some pages on it online. We want images. You can print them out and you can label it with the dimensions and information that you find out about it. Images, dimensions of the crater. And whatever else interests you. So this will be a great topic. It's one of the most dramatic examples of kinetic energy when an asteroid comes and collides with the Earth. So the idea is we have the surface of our Earth, and this asteroid will make it seem like a comet. It's about to collide with the Earth, and let's make the Earth a little flatter, okay? Just that section of the Earth. When it hits the Earth, all of this energy, remember, it came from work. It can be converted back to work. It can dig a giant hole, which is namely that crater. And we're also going to see it's going to create a lot of heat, but we haven't gotten to thermal physics yet. Major chapter in this semester. But yeah, asteroid collides with the Earth, gigantic explosion. And if you know how big this thing is, you can estimate the speed. Like I said, we know orbital speeds. And so you know how many joules are here. It's just a big number. If it blasts, if it collides and comes to a stop in a fraction of a second, then that's your T, and you can figure out how many watts of power it momentarily had. It just turns into a gigantic explosion. Good, so you guys will be in the position to understand it very systematically from everything we've done all the way down to this Arizona meteor crater and the collision that happened there some time ago. Good, so that's what we have for today. And go ahead and have a good look at this, see if you can get the good images, and we'll see you guys next time.